Now, we are going to discuss about applications of BIOT SAVART'S law. What are the importance of application of a BIOT SAVART'S law? With the help of applications of a BIOT SAVART'S law, that has a magnetic field at an axial point on the circular loop, we can constructed by a circular loops in an electric motors as well as a electric generators. Then due to this we can understand the direction of a current and introducing the direction of a magnetic field. Due to that, which is the face of the circular loop can act as a north pole of the magnet, then vice versa another pole is the south pole of the magnet. For understanding the current carrying circular loop or the current carrying conductor as a magnet, that magnets we can use as by the construction of an electric motors as well as electric devices. For that purpose we can learn the applications of BIOT SAVART'S law. The first application by the BIOT SAVART'S law, that is a magnetic field at an axial point of a circular loop. Loop means it consists of n turns. Consider a circular loop of n turns. It carries a strength of an electric current I. The radius of the circular loop, the center of the circular loop is O, and the radius of the circular loop can be capital R. On the circular loop we consider a small current element. That current element on the circular loop can be taken as a dl. From the center at a point of P, we can determine the magnetic induction. The distance between from the center of circular loop to the point P where we can determine the magnetic induction, it should be represented by the X. When it can be represented as an X, therefore we can line joining between the current element and the point where we can determine the magnetic induction, then it can be drawn like this. This is the line joining the current element and the point of a magnetic induction. When we can determine or drawn the point at a point P, here it can subtending an angle of pi. Therefore current element making an angle with the line joining as theta. Therefore at the center of the circle is a right angle that has a pi by 2. Therefore we can determine the distance of current element to the point P. It can be represented as a small r. Therefore we consider the O current element dl and the point P as a right angle triangle. We can apply the Pythagoras theorem. Square of a hypotenuse is equal to the sum of squares of other two sides. According to that, small r is equal to capital R square plus x square whole root. This is the distance between them. For the current element dl, then it produces a magnetic induction. That magnetic induction is a dB. It should be perpendicular to the current element dl. When it should be the perpendicular to the current element dB, then this current element dB we can resolve into the two components. Therefore, in a horizontal component of a magnetic induction dB at a point P is given by dB cos pi, and then a vertically component can be given that as dB sin pi. Similarly, we can take at a diametrical opposite end and another current element that has a dl. From this we can join the line intersecting at a point of P, making an angle of pi. When it is making an angle of pi, resolve into the two components. That two components of a resolution. One is that magnetic induction due to the current element. Another current element that can be represented as dB dash. This dB dash is resolved into the two components. One is a horizontal component is a dB dash cos pi. Here making an angle of pi. Then vertically component is a dB dash sin pi. Here you can observe in this diagram dB cos pi and dB cos pi. These both are horizontal components at a point P to determine the magnetic induction dB and dB dash. So therefore, when it is a point P determined to determine the magnetic induction dB and dB dash, these both are cancelled to each other. When these both are cancelled to each other, finally we can get the resultant magnetic induction due to either dB cos pi, dB cos sin pi or dB dash sin pi. The resultant magnetic induction at a point P due to a circular loop carries the current I can be given in a vertically component of dB dash sin pi or the dB sin pi. So therefore, according to the BIOT SAVART'S law, the magnetic induction at a point is given dB is equal to mu naught by 4 pi into strength of a current I dl sin theta is divided by r square is the separation distance between them. But therefore, the total magnetic induction B is equal to, that is due to a vertically component of a dB sin pi or a dB dash sin pi, the total magnetic induction B bar is equal to integral dB sin pi. When it is an integral dB sin pi, according to the BIOT SAVART'S law, we know the value of dB. Then substitute here, we get the magnetic induction. Then that magnetic induction, total magnetic induction B bar is equal to integral, the value of dB is mu naught by 4 pi into I dl sin pi, ideal sin theta is divided by r square into sin pi. Here mu naught by 4 pi is a constant, I strength of a current is a constant, then the length is a various theta and r square. All the constant terms we can take into the outside. Here we can observe current element dl and the magnetic induction dB at a point P are perpendicular to each other. When those are perpendicular to each other, angle between them theta is equal to 90 degrees. That means current element dl is perpendicular to the magnetic induction or the line joining the point dB. So the theta is equal to 90 degrees. Then substitute here theta is a 90 degrees. Therefore sin 90 is equal to 1. So a constant value mu naught by 4 pi into I by r square into the sin pi integral dl. Integral dl. From the diagram, ODLP is a right angle triangle. In this right angle triangle, we can determine the value of a sin pi, which is equal to pi opposite side, that is a capital R, by a hypotenuse is a small r, which is equal to capital R by the value of a small r. From the diagram, it has a root over capital R square plus x square. When we can determine the value of a sin pi, then integral dl. Integral dl means the total length of the circular loop. It can give integral dl is equal to its circumference of the circle of radius capital R is a 2 pi r. Therefore, the magnetic induction B bar is equal to mu naught by 4 pi into I by small r square. The value of a small r is r square plus x square whole square and root get cancelled. It remains r square plus x square into sin pi. Sin pi is a capital R by root over r square plus x square into integral dl. Integral dl is 2 pi capital R. 2 ones are 2 twos and pi get cancelled. That is equal to mu naught I r into r square is divided by 2 into here r square plus x square whole to the power of 1. This root can be written as r square plus x square whole to the power of 1 by 2. Then take LCM, we can get r square plus x square whole to the power of 3 by 2. Therefore, the net magnetic induction at a point P due to the current element dl or due to the current circular loop is given B bar is equal to mu naught I r square is divided by 2 into capital R square plus x square whole to the power of 3 by 2. This is the mathematical equation for the magnetic induction due to the current carrying circular loop on axial line at a point of P. When we derive this mathematical equation, then how the magnetic induction is various at this point, that's we are going to discuss in different cases. In 2 different cases we can discuss how the magnetic induction is various with the help of this mathematical equation. Finally, we can get magnetic induction or magnetic field induction B bar is equal to mu naught I r square by 2 into r square plus x square whole to the power of 3 by 2. This is the magnetic induction at a point of P due to a circular loop. From this, we are going to take different cases, such are case 1. In this case 1, I will go for if x is equal to 0. That means the point P is lies at the center of the circular loop. When it is lies at the center of a circular loop, then what about the magnetic induction? If x is equal to 0, then here we can substitute x is a 0 then magnetic induction B bar is equal to mu naught I R square is divided by 2 into this term becomes to 0 R square whole power 3 by 2. 2 ones, 2 2's get cancelled. Then we can get mu naught I R square is divided by 2 R cube. Here R square once R cube get cancelled remains R. That therefore induction we can get mu naught I by 2 into R. Therefore, the net magnetic induction at the center of the circular loop, net magnetic induction at the center of a circular loop B bar is equal to mu naught I by 2 into R is the formula or mathematical relation for the net magnetic induction by the circular loop at its center. At its center, the magnetic induction or the net magnetic induction B bar is equal to mu naught I by 2R. Mu naught I by 2R. This is the first case. Then I am going to discuss another case. With the help of the another case, I am going to define the magnetic dipole moment. What is that magnetic dipole moment? How we can define that magnetic dipole moment? Now I can go for the case 2. In this case 2, I am consider if R is far less than X. When I am considering R is far less than X, before going to take this relation, I am going to existing this term, that is that mathematical equation that as multiply and divided by both sides as a pi, that is equal to mu naught I into pi R square. Here I am multiplying, is divided by 2 into pi R square plus X square whole to the power of 3 by 2. Again here I can multiply with 2 and divided with 2. When I multiplied and divided by 2, it can be written as mu naught by 2 2's are 4 into the pi 4 pi into 2I pi R square is the area of the circular loop, can be written as A. When it can be written as an A, is divided by remains R square plus X square whole to the power of 3 by 2. That the magnetic induction at a point P, we can get that as a B bar is equal to mu naught by 4 pi into 2I into A is divided by R square plus X square whole to the power of 3 by 2. It is the mathematical equation for the magnetic induction due to a circular loop of 1 turn. Suppose this circular loop consists of an n turns, this equation can be written as mu naught by 4 pi into 2I into NA. N is the total number of turns, is divided by R square plus X square whole to the power of 3 by 2. This is the equation for the magnetic induction. From this equation of a magnetic induction, I can take another case, that is the case 2. So what is that case 2? The net magnetic induction B is equal to mu naught by 4 pi into 2 into total number of turns n and the current in each turn. It is said to be ampere turns into the current cross-sectional area A is divided by r square plus x square whole to the power of 3 by 2. From this relation, I can take the case 2, that is case 2. In this case 2, if x is far greater than r, then r is neglected, or r square is neglected. R square is neglected. When r square is neglected, therefore the net magnetic induction B bar is equal to mu naught by 4 pi into 2 Ni into A is divided by x square whole power 3 by 2. 2 get cancelled. That is equal to mu naught by 4 pi into 2 Ni into the A is divided by x cube. Let we can consider Ni is said to be ampere turns into the cross-sectional area of the conductor, is said to be magnetic dipole moment, can be written as a capital M. Product of ampere turns and the cross-sectional area of the conductor is said to be its magnetic dipole moment. Then magnetic dipole moment can be denoted as a capital M. Then substitute in above equation. Therefore, the net magnetic induction at a point of x or at a point of P at a distance of x, B bar is equal to mu naught by 4 pi into 2 capital M, because Ni into A is a capital M, by x cube. Therefore, according to this mathematical equation, we can conclude a current carrying circular loop. A current carrying circular loop acts as a bar magnet. When a current carrying circular loop acts as a bar magnet, then what is the north pole of a bar magnet? Then what is the south pole of the bar magnet? How we can understand the poles of the magnet? According to this mathematical equation, B bar is equal to mu naught by 4 pi into 2 pi by x cube. This is the mathematical equation for the magnetic induction of a bar magnet at a point on P at a distance of x on an axial line. Due to that, we can conclude or confirmed. So this is the magnetic induction due to the circular loop. So that this circular loop act as a bar magnet. So when it is act as a bar magnet, then what is the south pole and what is the north pole of this circular loop? Now we are discussing south pole and north pole of this circular loop, because of current carrying circular loop act as a magnetic dipole. When it is act as a magnetic dipole, then it produces magnetic dipole moment, or the magnetic induction B bar is equal to mu naught by 4 pi into 2m by x cube. We must discuss about the poles with respect to the direction of current. With respect to the direction of current. Then what is it? Now we are going to discuss the direction of current. Then we can understand here magnetic induction at a point P on the circular loop, a distance of x. That magnetic induction B is equal to mu naught by 4 pi into 2m by d cube. Here m is the magnetic dipole moment. Dipole moment can be defined as product of ampere turns and cross-sectional area of the conductor, or the circular loop is said to be its magnetic dipole moment. So that current carrying circular loop act as a magnet. So we can determine the direction of a current and the poles of the magnet. Let us consider current carrying circular loop. It is the current carrying circular loop. Then it carries the current, clockwise direction. When it carries the current, strength of a current is I, clockwise direction. Then what happened here? We can observe when it carries the current of a strength I in a clockwise direction, we can represent the clockwise direction of a current. This is the clockwise direction of a current. When we can represent the clockwise direction of a current, join these both tail ends of the direction of the current. When we can join both tail ends of the current here formed by the south pole, if current is enter in a clockwise direction for the circular loop, current is enter clockwise direction to the circular loop, it acts as a south pole. When it acts as a south pole, therefore is the magnetic induction. This magnetic induction, the direction of the magnetic induction from the point P to the center of the circular loop, to the center of circular loop. This is the based on to the direction of a current in the circular loop. In the first case, when the circular loop carries the current in a clockwise direction, due to the clockwise direction of a current, here it acts as a south pole of the magnet. Then the direction of the magnetic induction from the point of P is a radially inward direction. This is the first case. Then the second case. Then what about the second case? Is a circular current carrying conductor. When it is a circular current carrying conductor, then it can carry the current in a anti-clock direction. When it carries the current in a anti-clock direction, this is the direction of a current in a anti-clock. When it is the direction of a current in a anti-clockwise, join the tail ends. When we can join the tail ends, here we can observe the N. N means north pole of the magnet. That means when a circular loop carries the current in anti-clockwise direction, it acts as a north pole of the magnet. When it acts as a north pole of the magnet, due to the north pole of the magnet, magnetic induction at a point P acts radially outward direction. So that due to the north pole of the magnet, the direction of the magnetic induction is radially outward. Due to the south pole of the magnet, magnetic induction is acting radially inward direction. These are the two graphical representation for the poles of a magnet according to the equation for the magnetic induction, that is B is equal to mu naught by 4 pi into 2m by x cube. So that a current carrying circular loop must be act as a magnet. That is, if it carries the current in a clockwise direction, the face act as a south pole and another face act as a north pole. Vice versa, if conductor or the circular loop carries the current in anti-clock direction, the first face act as a north pole, therefore another face act as a south pole. Therefore, these are the to understand a current carrying circular loop as a magnet. Thank you.